Hello, welcome to this talk on MySQL 8 at Booking.com. My name is Nikolai Plum and I'm a database engineer at Booking.com based in Cambridge. Our topics today are MySQL at Booking.com, how we use MySQL, and how our business works a little bit. And then I'm going to continue about how we're using group replication, how we're using MySQL to handle bigger data and interface with big data systems, and then how you can use MySQL 8 for mixed data models. So first of all, Booking.com. We started off quite small. We have quite modest origins. We started off with a quite small website. You can still find it on the Wayback Machine. It didn't look much slicker than this slide. We aimed to connect people to hotels, and then that was basically all we did. Now, today, we are a much bigger and much different company with many different technologies and many different travel products. Particularly important for the databases is that we book in 1.5 million room nights every 24 hours. We have 29 million kinds of accommodations and attractions and other things listed. We have 43 languages that we support. When it comes to languages, we started off with major languages and we moved down to smaller language. By the time you get down to Icelandic, you're talking about a language of 300,000 people. So at that point, dialects become more important. Portuguese in Portugal is a lot different to Portuguese spoken in Brazil. And Spanish in Argentina is quite different from the Spanish that's used in the rest of Central America or in Spain itself. So we have both dialect and language support. And we need to be able to present content to customers in a way that they find easy to read, because the easier it is to read it, the more likely they are to book an accommodation or an attraction with us. To power all this, we've been using MySQL for 15 years, more than 15 years. We're using it for core transaction processing, and in fact, all over Booking.com. Everything in Booking.com is powered by MySQL one way or another. The questions arise like, why did we do this? Why did we choose MySQL? So the main reason was read scale out. If you need to read a lot of data, MySQL has a very compelling replication model. It's had it for a long time, even when other products did not have a good replication model. It's also very fast, read speed out perhaps as well. It's very fast, especially for a connect, transact, disconnect model, as often happens on the web. It's also very reliable. It's very reliable these days. It's actually quite hard to crash MySQL. We haven't found a crash bug for a while. It used to be a lot easier to crash, but the engineers now at Oracle and at Sun before them greatly improved the engineering quality, and many of these people have been working on MySQL for a long time, and they've been making it an extremely reliable product. If you look at the internals, they're very predictable. It's easy to understand, and it's easy to fiddle with the internals, and if you have to do some emergency maintenance, you can do that, and it works pretty successfully. So from an administration point of view, it's very nice to handle. We started off using MySQL 4 back in the day, but now we're running a mixture of MySQL 5.7 and MySQL 8, migrating towards MySQL 8. When you have an online travel business, you get quite a data mix. We have a mix of data, so there are data sets that have many reads and a few writes. Things like the product catalog, reviews from customers, reference data, things like currency names and airport names and that sort of thing. And then we have data that has to be read and written with low latency. Things like inventory while you're actually making a reservation, processing payments, processing finance information and invoicing and so on. And also messaging. When you have an online chat function or you're trying to send somebody an email or an SMS, this has to be snappy. It has to happen very quickly so people get a good interactive response. We also have logs, analytics, archives, larger data for experiments in marketing. Booking.com has an intensive culture of experimentation, data-driven experimentation on the website. So if we put something new on the website, we have to keep track of what's going on there, whether people like it or not, so we can see how to improve our website. Because of all this, we have a lot of MySQL. We have to manage this at scale. And the only way we can manage this at scale, at large scale, is relentless automation. So we have to automate the process of making new databases, making new database schemas, replacing broken instances. Machines break down, hardware breaks down. MySQL doesn't break very often, but the hardware breaks down more often. We have to patch things, we have to upgrade things. Everybody has to patch and upgrade for security reasons and compliance reasons, and also for feature reasons, so we can bring users new features, we can bring them MySQL 8. We also need to auto-scale our pools of replicas for business needs. If products become more popular, we have to scale things up. If we manage to optimize something, maybe we can even possibly scale down a little bit. We have to handle things like data center infrastructure upgrades. We even have to do things like patch firmware in the SSDs and the disk controllers. You know, it's computers all the way down these days. So yeah, and all those computers have software and they will have patches that you need to apply to them. So when we're managing MySQL, some of the software we use, for example, is Orchestrator. You can find Orchestrator at the URL at the bottom of the page. Well, I'm not going to talk in detail about how Orchestrator works, but Orchestrator manages connection of our topology, so making sure that everything is replicating from everything else. The layout that you see here of servers in one of our actual installations is a diagram that is shown in this diagram here. So we have a master layer at the top. We have standby masters and binary log read scale out, and then we have a read layer at the bottom. Applications read from the read layer. We need the middle layer because if that master breaks down, we have to have another one ready to take over on standby. And also because if you connect very many replicas to one master, you can run out of network bandwidth or CPU. So we need several of them because we can have many hundreds of replicas sometimes on some occasions. You can scale this up almost indefinitely, by the way. You know, I wouldn't recommend it as a design, but you know, you can easily put over 1,000 replicas in this sort of setup without any problem. But now you're managing this, and Orchestrator itself has a database to manage the database. So what you end up with is that its database is all the way down. Your management tools use MySQL, but if the MySQL in your management tool breaks, then it can't manage the rest of them. So the Orchestrator database must never break. Otherwise, we have a circular dependency where Orchestrator is trying to repair itself, and it can't do that properly. So we wanted a database that would never break down, which is a tall order. Not something we've ever had in our experience before. So if you want an unbreakable database, how do you get that? You want it to be non-stop in the short term. In the long term, you can always go and repair it, but in the short term, it must keep working. So you tend to reach for a clustered database, because if you have a cluster of databases where they're all a cooperating group, then they keep working after one instance fails without any intervention. You will need to fix it eventually, and you can have automation that will fix it in the background. But at any particular time, if one of the servers breaks, your clustered database will keep running. And that's how we manage to have Orchestrator running on a database while repairing all the other databases. Essentially, what we've done is we've replaced break-fix reactive maintenance. It broke and we fix it. Whether that's manual, you get paged in the old-fashioned style, or automated, like something reacts and fixes it, with preventative maintenance. Building things, reliability engineering our systems so that they do not break. We have to do maintenance to repair them and so on, but they don't break and then they fix, they just keep working. If you can do this, then your life will be much easier. And you are also not reliant on the fixing working every time, because the problem with trying to do some sort of break fix is that if the fixing fails, then things remain broken and now you have an even longer outage. Whereas if the fixing doesn't work with your preventative maintenance, you get paged about it, but the customers do not notice an outage. So this is really the most important thing I'd like to say in this presentation. Try and replace your reactive break fix with preventative, proactive maintenance and reliability engineering. We're doing this with MySQL 8 and group replication. So group replication in MySQL is a cluster with consensus, a cluster of servers with transactions that have unique identifiers. They're using the Paxos consensus protocol to achieve consensus between them and agree on what transactions to process and which transactions not to process. You can read all about this in the MySQL documentation. There's an extensive description of how the consensus works. For our purposes, we have one primary writer and several readers in our group. Any one of the group can take over, but you can read from several members of the group. You should only write to one of them. It's technically possible to do multi-writer, but it adds a lot of complexity. Especially what happens is that if you have transaction into one side and transaction into the other side, then when they meet in the middle, if they disagree, one of them will be failed. And the application sees this, that commit fails. But applications are not used to this. They are used to begin transaction, do something, commit, and then commit like never fails. They handle it very badly. So it adds application complexity to handle a greater chance of transaction failures and having to back out and retry. So I do not recommend having multiple primaries, just have one primary. There's also a problem that if you're doing DDL, changing your data model and your schema in one side of your group, and you have DML, an update, in the other side of the cluster, then you can lose the cluster, lose the write during the DML, so don't do that. Groups can only be of a certain size. You shouldn't have groups that are too big. So in order to get the scale out that we need, we use standard binary log replication, usually async replication for us, for scale out. Our groups span availability zones. You want to do that because then when one of your availability zones has a catastrophic failure, the other members of the group in the other availability zones will be able to gain consensus, form a quorum, and continue processing transactions. We prefer MySQL 8 group replication. It is available in MySQL 5.7, but 5.7 is not getting a lot of new features these days. New features will tend to get added to MySQL 8, so I would strongly recommend that you use MySQL 8 for your group replication. Having used group replication to try to make your database unbreakable, you end up with something like this. You can see that the master up at the top has been replaced with the replication group acting as a single master, and we still have binary log replication out to replicas, and the applications talk into the group. As you can see, the write transactions go to 1, but if you have a need for high reliability reads, say, for example, transactional reads, then you can read from the group as well. If you have reporting or display needs that are not critical, then you want to read that out at the bottom of your replication, your standard replication chain, to avoid overloading your group too much. If you don't have a lot of reads and writes, just read and write from the entire group. Replicas are also needed for things like taking backups, that sort of thing. We did have to build some additional in-house technology for this. If you have your primary, you have to be able to find your primary. You have to know what the members of the group are. And of course, it's not going to be a single server. The primary can move around and you might replace this. You need some service discovery. We have in-house service discovery for both the writer, the writable primary, and the readers using Zookeeper, which works very well. I mean, Zookeeper is another database that's highly reliable with consensus and so on. The thing is, Zookeeper is only for storing a very small amount of data. You can't do your financial transactions in Zookeeper. That's just not what it's made for. We have some technology to auto-repair. If a group loses communication with a group member, it will try to rejoin it, but it won't always succeed, especially if the group member was offline for a long time. And obviously, if the group member dies completely, the hardware is just gone, you need to make a new one and join it to the group. There is automation to do this, but you have to trigger this. And so we have automation code that runs in the background and does this in the background proactively, because we're trying to be proactive and not have a break-fix scenario. We also, of course, have to do upgrades and patches. If you want to patch or upgrade a machine, you force a new primary to move the primary around. You take the old primary. You can take it away and upgrade it and put it back, or you can add a new one and remove the old one if you want to cycle through the hardware. We have a general preference for replacing machines from the stock of spares from our provisioning infrastructure, rather than reinstalling the same machine in place, because that gives the network engineers and the data center engineers a chance to take the machine away and do something with it, like move it between racks or something like that. You also need some topology management. I mentioned Orchestrator. Orchestrator can manage its own topology as long as the master stays up. So you need to reattach those replicas, because the replicas replicate from one member of the group, and they can use any member of the group, but they do pick one, and you have to move them to a different one if if that member of your group breaks. We've had some pretty good experiences with this. It's easy to set up. If you want to set it up for testing, use the MySQL shell. It's extremely easy to do. There's a great tutorial from Lefred at Oracle. There's a URL there of the tutorial you can see on YouTube. There are many other tutorials online. It's very easy to set this up. There is a latency increase, which is mainly because of having to gain consensus across your availability zones. You have to make sure your applications can handle it, but in the normal running scenario, when the group is up and running and everything is happy, which will be the situation nearly all the time, there are some optimizations that make this delay less than you might expect. So don't be afraid of the delay, but just do check you can handle it. You can also use group replication to establish a quorum for other applications. If your group has a working primary, then it has the quorum, it has the majority of servers. So you can use this to establish whether your availability zone is the surviving zone, if you have a network split or something like that. So we are actually using group replication to occasionally have a software application that needs to know whether it's in the main data center or the secondary disconnected data center. And you can use this to get the quorum. So you can get quorum service for free. Pretty much, this all does what it says on the tin. It's a pretty solid product, actually, in our experience. In terms of managing this, distributed system management complexity has always been with us. Even your MySQL standard master with some replicas is a distributed system with eventual consistency and other distributed management issues. You do have to monitor this system state and fix it before it degrades too far. Group replication is very reliable and predictable inside its design limits, but it's much harder to fix outside its design limits. So if you get into a situation where many of your group members are dead, then it can be difficult to fix. So it is well worth having the monitoring infrastructure and the automation infrastructure to repair your group automatically. And because of that, group replication has to be integrated into your system management frameworks. You have to build alerting and provisioning functionality around group replication that you already have for your standard MySQL. This is work you cannot avoid. Once you've done this, it works great, but it's not a free lunch. It's just a tasty lunch. So in conclusion for group replication, it's good as a high resiliency database for small clusters, just the group. It's good as a high resiliency core of your larger database topology. Core that works very well, replicas that have a lower availability between individually rather. It's very easy to set up. Basically treat it right and it will treat you right. Our next topic is data processing at scale. So we have quite a lot of data. MySQL is very good for interactive user data. Like it's a great database to connect a website to. It's good at small data, very small individual transactions, very fast. And overall, in terms of modern data systems, it's a medium-sized system. You can take it fairly big if you want to, but it's kind of fundamentally medium-sized, terabytes, basically. On a good. Beyond terabytes, things get a bit stressful, so terabytes. Meanwhile, Hadoop, and I'm going to talk about Hive, not HBase or other Hadoop technologies, but Hadoop and Hive are not responsive for interactive use. It takes tens of seconds to return a response to any query, even the simplest one-row response. So it's not suitable for connecting a website to. It's better at large data. If you want to store very big data objects in Hive, it works fine. And you can build a mind-bogglingly huge system. Petabytes are easy. So how do we unify these? We have a lot of data, but we want to be very responsive. What we do is we have some batch processing, some machine learning, data imports, and so on. Sometimes that data even came from MySQL in the first place. We transfer it over to Hive, or we use it as the data source for a machine learning model. All that crunches away and does some reporting or some learning and so on. And then we materialize the results in MySQL tables again. And then we connect our website to the replicas of this database and show the user the results on the website and make a profit. Users love this. We end up with a rich user experience based on lots of data processing, and we show it to them very quickly, and people love this. But you have a lot of updates in your MySQL here, and this leads to challenges. many frequent updates, possibly sometimes an entire table refresh. Machine learning models are particularly good at this because they crunch on some data and then they give you a whole pile of numbers that are very slightly different numbers from the ones they gave you last time you ran the model. So if you feed this into MySQL replication model, MySQL has a binary log generated on the master, which is copied to the replicas and applied to the replicas. So it's an output queue, transfer, input queue. But if you are updating a table, you're storing the table, and then you're also storing a copy of all these updates in the binary log, and you have to keep them around for a while for delayed replication and other things. Sometimes you might even have a new table, an old table, and a binary log of rights to the new table. And you can try an in-place update. You can even try compressing the tables. If lookup speed is not very important, then you can compress the tables. But actually, if lookup speed is important, don't compress the tables. But you've still got these very large logs that keep accumulating with many copies of your data. You know, if you're refreshing this table once an hour and you're keeping your logs for several days, you're going to have tens of copies of your table in the log, and the logs will totally dominate the system and eat all your disk space. So, looking at the binary log data, you know, where the space problem lies, and also the binary log is the part that's under the control of the database engineers because the users control the data model in Booking.com. So we can't easily ask them to store less data because the data is what makes the money in the business. The binary log kind of doesn't make any money, so we'd like to make it as small as possible. And so the binary log contains replication event data, which is like which table was modified, the time, who did it, the transaction ID, and all that sort of thing. And then it contains actual row data from the tables, what was changed, what was inserted. And the replication event data is very compressible. The binary log protocol is quite chatty, quite verbose. If you take your database and you run MySQL bin log on one of the bin log files, you can see there's an awful lot of repeated data in there. And that is all very compressible, compresses extremely well. Row data compresses, depending on what kind of data it is. Text and JSON compress very well. You know, plain numbers also compress very well. So if we have text of somebody's review of the hotel, or we have a JSON object of a transaction information, that compresses very well. Things like UUIDs and hashes and so on, they compress less well, but they still compress. JPEGs obviously don't compress at all. I'd honestly have to ask why you're storing a lot of images in MySQL. If you want, you can do that, but perhaps you should consider some sort of object store for that. But then if you have an object store full of pictures, you're going to need to store structured metadata about that, and that can live in your MySQL database. So the history of binary log compression and how to do it. This has been a requested feature for a long time. The first feature request from 2009 to MySQL. There were lots of early add-on attempts. Somebody thought, I know, I can gzip the bin log, that'll be great. I'll uncompress it when I need it, which only works if you know you can uncompress it, and then you have to manually or have some extra external code that uncompresses and recompresses the binary log. If the database happens to look back to the transaction that's in the log that you compressed, it'll fail. Replication will stop. And that causes all sorts of breakdowns. And this is basically not sustainable. These are all kind of non-production level hacks. So handling transactions and handling replication requires fine-grained compression. It's really best done in the database. And if you want to be able to start replication and go back and pick a transaction out because you're catching up in replication, then each event has to be compressed separately. So this is really only possible in the database. So it's good that Oracle has implemented this in the database. When you're using this, don't forget the monitoring statistics are in the performance schema. This will tell you how much you're compressing. As usual with performance schema, there's a great deal of information in there. And if you read the manual carefully, you can find out how to use it. The overall statistics, though, are not very complex. And mostly what you're probably looking at is just the compression ratio, see how it's doing for you. So our experiences with this are that it can save 75% or more of your disk space. the savings can be dramatic. It also saves network bandwidth because the events are actually transferred in compressed form. If network bandwidth is a serious issue for you, this will be beneficial. We honestly haven't noticed a difference. It's really more about the disk space. So if you have the ability to store more logs, you can obviously have a longer log retention, which can be handy, longer audit trail, etc. But what you can also do is you can store the row query event with row changes. So back in the day, when we had statement-based replication, the statement was written to the log. So when somebody did something to the database and you wanted to know who did it, or where the damage came from, you could find the statement, and then you could look in the application code and find where that statement came from. And correlating changes in the database through the statements to the user who issued the query and so on was very easy. But now we have lots of problems with this because row changes are difficult to attribute to SQL statements. So you now have the feature that you can store the row query event, which means that there's an event for documentation purposes saying these row changes came from this query. But some people say, well, that uses extra log space and we haven't got the log space for this. But if you compress the logs, you can have the row query event. And then as a database engineer, your life will become much, much easier. Overall, using the binary log compression, we've found it has minimal extra overhead. The logs get smaller, and that's basically just how it works. The overhead of compression in terms of CPU is not noticeable. In particular, with modern computer systems, the compression code is faster than marshalling and unmarshalling this data to and from network devices or disk devices, assembling TCP protocols or SATA protocols or other protocol overhead. So if you compress the data, you spend more time compressing, but you spend even less time moving data around to and from the I/O subsystem, the network. So overall, this is a win, and you should not be afraid of the overhead of compression in this case. It's also very easy to configure, and in particular, if a host somewhere in your replication setup is not accepting compressed logs, this will work properly. Certainly, you can migrate from one to the other very easily. So binary log compression, fundamentally, I would just recommend using it. The next topic I'd like to talk about is the document model and mixed data models. So MySQL has had JSON as a first-class data type for a while. But in MySQL 8, its efficiency has been greatly improved. Replication efficiency is much better because previously, when you updated a JSON object, the whole thing would be copied in the replication stream. And if it's a big object and a small change, that is a significant overhead. Now, only the differences are passed along, only the changes to each value in the JSON structure. It's sort of a bit like row-based replication pushed down. It's also faster in general. Accessor functions have been improved. There has always been JSON structure validation in the database. You've always been able to stuff JSON data into a text column, but now you get it validated. There are lots of details about this in the MySQL reference manual. The JSON section of the manual is actually quite good. There is also a document-oriented interface, the X protocol, where you can treat MySQL entirely like some sort of NoSQL store, except you have the reliability and the performance of InnoDB behind it. But I'm talking about the mixed model, which is even more powerful in an established yet agile business that wants to adapt and change rapidly. So here's an example of what you might do. So here, for example, is the JSON that you might get back from a payment provider if you are whoever's handling your credit card payments. You get back a blob of JSON with all sorts of things in it. If you want to have the best of both worlds, you can split this data into the stuff that you really care about, that you want to index, that you want to have perhaps enforced that it's not null, and put this in the relational part of the model over there. And then over here, you can have the transaction information and the payment identifier in this case, and all that other kind of thing. And some of this is quite variable, and it varies by which payment provider you're using. So in this case, we've got the relational model for the essential data and the stuff you want to index and so on, and the JSON for kind of optional data. So what we've got is we've got the relational fixed structure data and the JSON variable structure data. You can even index virtual columns extracted from the JSON fields if you feel like you want to index the JSON. And if the JSON doesn't have the value, then your index just has a null in it. And the particularly valuable thing about this is that if you already have a well-established data model with code that is using this data model, but new code needs to add and retrieve new data while existing code keeps running, you can extend your existing data model with documents by adding JSON columns and still retain all the performance and advantages of your existing data model. So, I hope that these examples have been useful to you and you can apply them in your business. I think I have time to take a few more questions while we're online, so I'll cover a few of the popular questions here, and then more questions will be answered in the other Q&As. So question about what sort of hardware are we using? What sort of cloud provider are we using? Well, our hardware platform at the moment is a mixture. We use a variety of cloud providers for various purposes. We also have a significant on-premise installation. On a very large scale, on-premise can have some significant advantages over the cloud, and cloud can also have some advantages. So we are actually mostly using bare metal for our databases. Virtualization is not a very large win if you have a very large number of machines and very large number of replicas, because you have to manage a lot of instances, and we have a very high quality provisioning infrastructure built by teams of colleagues. So we're mostly using physical hardware at the moment, 1 to 8 gigabytes RAM, 32 cores, sort of medium-sized hardware. Size varies a little. That sort of thing generally works well for us. Right, next question is, how many MySQL servers are we managing? Thousands, can't say exactly, I'm afraid. Also, next question, so are we using InnoDB? Yes, we are. Everybody should be using InnoDB. I mean, by now, InnoDB is, you know, it's completely the standard, and you should not be using MySQL or anything else. So yes, of course, we're using InnoDB. Everyone should do that. All right-thinking people should use InnoDB. Right, next question, please. Our management software. So I mentioned that we use Orchestrator, and over in the provisioning side of things, we use things like Foreman, and we use a collection of open source software and other software where it makes sense. I'm afraid I can't share our automation framework. It's very specific to Booking.com. And in the end, when you're building a large infrastructure, you do have to kind of write the glue between the components yourself. And we have done that in a Python application as is traditional these days. So I'm afraid I can't share that. So what do we use to install our servers? Well, as I mentioned, you know, we're using Foreman, we have some automation framework and so on. We have automation that installs a basic CentOS install, and we're doing our system management mostly with Puppet. So Puppet manages the operating system, and our in-house administration tool manages MySQL with the assistance of things like Orchestrator for some particular tasks. Right, next question. So how many MySQL 8 servers do we have? Quite a few. Can't say, I'm afraid. That kind of things, I'm afraid these numbers are commercially confidential. But we have an increasing number of MySQL servers, and in particular, we are using it both in our infrastructure for our management applications, and we're also using it near our front end. One of the applications that we found particularly useful is that MySQL 8 has a brand new GeoDB infrastructure. So, well, geodata infrastructure, which has been completely rewritten. And we are taking the opportunity to improve our handling of geodata to make it more efficient. So MySQL 8 has been taking a leading role there for quite a while now, actually. So are our servers PCI, SOX, GDPR compliant? Yes, we are compliant with all these things as we have to be. There is not a problem with making MySQL PCI compliant. Some people think you can only do it with other databases, but no, you can make it PCI compliant, you can make it SOX compliant, you can make it GDPR compliant. You just need suitably skilled people and a good QSA. Right, next question, please. So at the moment, actually, we don't have any more questions here. I think some more questions are being answered in the chat by my colleagues. So thank you very much for coming to my talk and listening to it. If you have any more questions that you'd like to ask me, do feel free to email me. My email address is here on the page.